Alright, boys, let's check out in-class problems from today, which is October 30th, which is the final lecture before the exam. So I already showed you this one. Okay, here's our reaction of HF being a weak acid with water. We have aqueous HF plus liquid water gives me hydronium ion, or H3O+, plus, which again is essentially equivalent to just an H+, plus that's aqueous, and an F- aqueous fluoride ion. So then my Ka, I just put in all the aqueous things, products go on top, reactants go on the bottom. There's no exponents that go anywhere for this one, so it's pretty straightforward. Okay, number 2, we said we have this much volume, let's call that V1, of this solution of a certain concentration. Why am I going ahead and labeling these M1, V1? It's because it says it's diluted, and this is our, remember we have our equation for a dilution, M1, V1 equals M2, V2. Okay, because M1 times V1, this is moles per liter times liters, that'll just give us moles. So if we're just diluting a solution, our moles that we start with should be equal to the moles that we end with, if all we're doing is adding more solvent to it. We're not changing how much of the compound is actually dissolved. So we have this much volume of this solution, we add more water to it, we want to know what is the new concentration. Okay, and for this we're not taking into account any kind of equilibrium process, any dissociation, or any loss of HF turning into these ions. We just want to find what's the total amount of HF in the solution. Excuse me. Okay, so M1 we said was 0.2 molar. V1 is 22.4 milliliters. M2 is what we're trying to find, and then V2, we got to be a little careful here. V2 is not 50, it's 50 plus the initial 22.4 that we started with. So V2 is 72.4 milliliters. So if we divide this out, I guess I should actually put this in my calculator since there was a thing, and no, that's not right. 0.2 times 22.4 over 72.4. Okay, that's definitely not right either. We get M2 is 0.06. We can go to 3, we can only go to 2 sig figs, so 0.062 molar. Okay, or 6.2 times 10 to the minus 2. Okay, now we said we reach equilibrium in our diluted solution and we measure the pH as 2.765. So how do we find the H plus concentration? Well, we know pH is negative log of H plus. If we're given the pH, we want to cancel out the log. We go 10 to the raise to the power both sides to get rid of the log. We also have to bring the negative over here, so we get 10 to the minus pH is our H plus concentration. And we said our pH is 2.765. So this should give me an answer eventually. Error, don't you, what are you talking about error? This stupid thing. There we go. This gives me 0.00172. Remember, we lose a sig fig. Basically, the reason that we lose a sig fig is because one of these sig figs, this first one, this first sig fig is going to sort of be reflected in our power of, that's not right, sort of be reflected in the magnitude of our answer, just in the power of 10. Okay, so we get 1.72 times 10 to the minus 3. Okay. This number basically says our exponent is somewhere between 10 to the minus 2 and 10 to the minus 3. So we're a little bit towards the 10 to the minus 2 side, right? If this was 10 times 10 to the minus 3, that would be 10 to the minus 2. So that's why we lose a sig fig when we take 10 raised to a power. Okay, calculate HF at equilibrium. So right now we have our concentration of H plus down here. We know that initially, before equilibrium, so let's say pre-equilibrium, that we had a concentration of HF we found from the first part of the problem is 6.2 times 10 to the minus 2 molar. And then we know at equilibrium, we know our concentration of H plus is this that we just found from the pH. So we also need to know, or we also know what the concentration of our fluoride ion is, because every time we get an H plus in this reaction, we're also getting a fluoride. So it's basically saying when one of these dissociates, we get one H plus and one F minus. So they always come into the reaction together, so their concentration should be the same. Now, how do we find the concentration of HF? Well, it's exactly what I said up here. If we're making H plus and F minus, it's because we're losing HF. This HF molecule is dissociating into one of these and one of these. Excuse me. So every time we get an H plus or every time we get a fluoride, we're losing one HF. So our HF concentration then should just be the starting amount of HF that we had minus however many moles of HF turned into F minuses or turned into H pluses. You could think about it that way. So 6.2 times 10 to the minus 2 molar minus this change in concentration because we're forming fluorides, or we could think about this as forming hydrogens. And this gives me This gives me 6.03 times 10 to the minus 2 molar. Now, really, since we only knew this to 2 sig figs, we can't go to this third digit here. So this would just be 6 molar. Now it says calculate the Ka and the pKa, which we maybe don't quite have enough room on here to do that now. Let's just bring this guy out. Okay, so if we want to calculate the Ka and the pKa for this problem, let's get everybody in the frame. Well, we said earlier Ka is this. Okay, so we just plug everything in, which would be 1.72 times 10 to the minus 3 molar. We said the H plus and the F minus are the same, so I'm just going to square that to save myself some time. And I get let me type that in again, just to make sure. I get an answer, okay, but we are a little dubious of this answer, but I guess I know the reason why this is actually. So we get 4.93, or really just 4.9 times 10 to the minus 5. Now, this is not the actual Ka for HF at 25 degrees Celsius, but I didn't tell you what the temperature was, so this is our Ka for whatever temperature this problem actually was. Okay, there's our Ka. Then pKa is just the negative log of Ka. So negative log of that answer is 4.3. Okay, next question. This asks us, it tells us the Ka of acetic acid is 1.7, well, let's get in the frame. It tells us the Ka of acetic acid is 1.75 times 10 to the minus 5th. And we just said for our last one, we showed our calculation on the side, and we said it was 4.9 times 10 to the minus 5 was our Ka value. Now this is asking us who is the stronger base, acetate or fluoride. So we need to kind of consider what these two reactions are, and I'm going to call acetate just HAC. Actually, let's call it HOAC because I feel more comfortable with that, and HF. So here's the Ka reactions. Now we just need to compare, okay, which one is the stronger acid, we can get that from comparing their Ka values. This one, Ka is 1.75 minus 5. So the stronger acid should be the one with the larger Ka value, right? Because that means we're forming more H+, we're getting more dissociation. So HF is the stronger acid, and remember, the stronger the acid is, the weaker its conjugate base is going to be. Okay, so in this case, HF is the stronger acid, so F minus is going to be the weaker base. Basically, this is saying the fluoride can't hold on to the H as well as the acetate can. That's why HF is a better acid, has a larger Ka value. The flip side of that is, if the acetate's holding on to this proton better, that means this acetate is going to accept a proton more readily than the F minus will. Alright. Now, let us continue on. Let us continue on to finish this thing. Okay, yeah, last one on this front page. We've got, if we add calcium acetate to HF, okay, and we form calcium fluoride and acetic acid, which way does the equilibrium shift? Well, two things are going to happen. We're going to be removing fluorides from solution. We're also going to be removing some of the protons from solution, because we just established on this last problem that acetate is a little bit better at accepting protons than fluoride is. Okay, so we're going to be removing two things from the right side of the equation. Okay, we're removing H+, we're definitely removing a lot of F-, removing much more F- than we are H+. But in either case, we're removing products, so we're going to have to shift to the right. Okay, shift right. Get more of this in the frame if possible. Alright, I don't think I'm going to have time to do this all in one part, so let me, well, shoot, we got lab here in like 10 minutes. Let me try to run through the second page real fast before lab starts. So I'll see you guys in part 2.